Assalamu alaikum. So far in the course, we had been looking at one-dimensional problems. But what we had done by using these 1D problems as an example is to completely see all the steps that were involved in the finite element method and how to formulate the FEM, how to set up an FEM problem for a given partial differential equation. However, real world problems, of course, 1D से ज़्यादा complicated होते हैं. They tend to be in higher dimensions. So slowly we are now going to start moving towards higher dimensions ताकि हम लोग ज़्यादा real world problems को consider कर सकें या फिर different problems को consider कर सकें rather than just the 1D. बट प्लीज़ नोट अगेन लेट मी रिपीट कि जो हमने 1D एग्जाम्पल्स कंसिडर की थी उससे हमने पूरा का पूरा मेथड ऑफ द FEM फॉर्मुलेशन को अंडरस्टैंड कर लिया है. ठीक है जी. सो हम बेसिकली वही सारे स्टेप्स जो हमने 1D में किए थे उनको सिर्फ हायर डिमेंशन के अंदर इम्प्लीमेंट करेंगे. ओके ग्रेट. So this is where we're starting off today. So today we'll be looking at a two-dimensional problem which will be actually the problem of heat transfer. लेकिन इसके अंदर भी I want to emphasize actually कि when we start to move towards 2D or 3D, we can actually look at either scalar field problems या फिर vector field problems. अब ये scalar और vector field से क्या मतलब है? This basically means कि हमारा जो field problem है, so for example हमारी axial loading के अंदर that was the displacement which was a scalar in 1D. whereas अगर हम 2D में आ गए हैं तो already हमारे पास variables हो सकते हैं जो कि या तो scalar हैं या फिर vector हैं. So initially we will start off by considering a field problem जिसके अंदर जो field variable है हमारा that will be a scalar, which is why I'm starting to look at the heat transfer problem wherein the scalar variable of interest is the temperature. Okay. So that's basically an introduction for this problem. Please note that this is taken from these sections right here from Fish and Belitsko. So do go through these from the textbook for a better understanding of what's happening in the lecture slides. So as we're moving to 2D and 3D or to higher dimensions, we need to actually do a little bit of revision of vector calculus essentially. So I'm sure you all recall that in 2D हमारे वेक्टर वेरिएबल्स जो होते हैं उनको हम represent करते हैं by their components in the individual basis direction. So I और J अगर मेरी basis vectors हैं या basis directions हैं तो उनके अंदर this vector Q will take a component Qx and Qy respectively, such that I can write it out in this notation right here or in matrix notation or tensor notation like so. Now there are many operations that can be performed on vectors. One vector operation that we can perform is to take the scalar product or the dot product of two vectors. Now the dot product is represented by this dot right here, written in matrix form. Then we can write it as the transpose of the first one times R. This will pop up again and again, so please do recall that the dot product can also be represented like so in matrix notation. Okay, and that basically is the product of the individual corresponding terms added together. Okay, I think everybody knows what a dot product is, so I can move on. Now, there is an interesting operator basically that will pop up again and again in our course, so it's worth mentioning it again. So there's the gradient operator or the del operator, जिसके अंदर basically we're finding the derivative of a given variable with respect to the x direction and with respect to the y direction separately. So this is known as the del operator and it's often represented by the symbol nabla right here. अब ये del operator itself जो है that's also a vector, right? So अगर हम del operator apply करें किसी actual variable field variable के ऊपर, then there are a number of different possible things that could happen. So number one is कि consider कि हमारा field variable है ही एक scalar, for example temperature. Then if I apply the del operator to a scalar variable, I basically find the gradient of that field then in the x direction and the y direction. Okay, so this is for a scalar variable. लेकिन if I have a vector variable, for example flux, heat flux जो है that's a vector variable, या फिर velocity even, then I can apply the del operator in two ways. One is that I could take the dot product with the del operator, which gives me something referred to as the divergence of the vector field. So this is represented by, divergence is represented by div. So the div of the vector q is actually the dot product of del with q, which is then solving out this dot product gives me this expression right here. Again, noting I can write the dot product using matrix notation by using transpose of the first vector essentially. Okay, लेकिन वेक्टर वेरिएबल के लिए हम डेल ऑपरेटर को एक और तरह भी अप्लाई कर सकते हैं. वी कुड ऑल्सो फाइंड द क्रॉस प्रोडक्ट of the vector, cross product with the vector q. Now this then means कि हम del cross q को find कर रहे हैं. This is referred to as the curl of the vector q. For our the problems that we're considering in this lecture, at least, we are only concerned with the divergence of different vector fields, so इसलिए this is more important for us. Okay, right, so a little bit of review of vector calculus, and then I also need to review one other thing actually. So and in order to go over that, it might be helpful for us to formalize our domain and our boundary and so on and so forth. So you may have recalled we have discussed this previously, like in order to more formalize it, let me repeat this. So basically जो भी body को हम consider कर रहे हो, that is the domain that we're looking at, and we represent the domain by omega. ठीक है जी. अब इस domain का जो boundary है, right, this domain की जो boundary है, that is represented by gamma, capital gamma. Okay, so the domain is represented by omega and the boundary is represented by this symbol right here, which is capital gamma. So अगर हम 1D में थे, तो हमारा domain is basically the length, the entire length growing from 0 to L of this beam. और इसकी boundaries are just at x is equals to 0. ये वाला point right here is one part of the boundary, and the other part of the boundary is right here, x is equals to L. ठीक है जी, 1D में ये होगा. और recall कि we can always have this unit normal n which is pointing out of the boundary, such that अगर हम x is equals to L वाले point पे consider करें, then this unit normal is +1 it's pointing out of the boundary, whereas x is equals to 0 पे consider करें, then this unit normal is -1, again pointing out. Similarly 2D के अंदर हम कोई भी arbitrary body को मैं draw out कर सकती हूँ, then my entire body is my domain. ठीक है जी, and its outer boundary, ये जो ये बनी हुई है यूं, that is gamma. And at any point on the boundary, I will have my unit normal, which is pointing out of the surface, basically. So let's consider कि मैं एक किसी scalar variable s का s की divergence का integral निकाल रही हूँ. Basically, I'm finding the rate of change of s in the entire not the rate, sorry, it's not with respect to time, it's with respect to the entire domain. So I'm finding the change in s over the entire domain. If I integrate this over the domain, 1D में मेरा domain is just, it's an integration over x. So I find ds by dx with respect to dx. So integrating this, I clearly just get s at 0 and L. That is, I find SL minus S0. और अगर इसको मैं manipulate करूँ by writing down in terms of n, जो कि s at L was +1 and at 0 it was -1, तो ये जो minus है ये n के अंदर incorporate हो जाएगा, such that I can write this just as in terms of s multiplied by the unit normal evaluated at the boundaries, at the boundary. The reason for being able to write it this way, again I repeat, is because ये जो minus है, that is taken into account by this unit normal n, जो कि x is equals to 0 पे -1 है. Now this actually is a surface integral of Sn. मतलब के Sn integrated over the entire boundary. ठीक है जी. So we went from I'll come to this in a second. More details for this you will have to look up on your own. But basically the point is that we're going from a domain volume integral and transferring it into a surface integral. Okay. This can also, we've done this right now in 1D, but we can also, this also exists in higher dimensions, of course, or higher dimensions. I will not be going into too much detail about this. For a vector field Q, यही चीज़ कि हम domain integral से एक surface integral पे जा सकते हैं, that is represented by something like this. ठीक है जी. Where ये जो 1D में ds by dx था, that gets replaced by the divergence of the field Q, right? ds by dx then corresponds to, in higher dimensions, by del dot q, और इसकी integration over the entire domain can also be written in terms of the surface integral of q dotted with n. Now this time this part right hand side corresponding to this right hand side right here. Now this basically is the divergence theorem. और इसकी मैथमेटिक्स के अंदर जाने के लिए आई वुड रिकमेंड कि यू प्लीज़ लुक अप व्हाट द डाइवर्जेंस थ्योरम इज़. बट मैं आपको सिर्फ ये क्वांटिटेटिवली थोड़ा सा एक्सप्लेन कर देती हूँ कि व्हाट इज़ दिस बेसिकली. सो डाइवर्जेंस थ्योरम जो है ना, इट्स बेसिकली स्टेटिंग द लॉ ऑफ कंजर्वेशन एसेंशियली. सो इट्स एसेंशियली सेइंग कि किसी भी चीज़ किसी वॉल्यूम के अंदर, एक वॉल्यूम के अंदर डी ओमेगा, एक ओमेगा के अंदर जो टोटल चेंज है जो हमें ये इंटीग्रेट करके मिलेगा, एक वॉल्यूम चेंज इन अ प्रॉपर्टी इज़ जस्ट गिवन बाय कि कितनी वो प्रॉपर्टी उस डोमेन के अंदर फ्लो कर रही है थ्रू इट्स बाउंड्री. ठीक है जी. ऑफ कोर्स दैट मेक्स सेंस. सो फॉर एग्जांपल अगर मैं गुब्बारे के अंदर if I'm blowing a balloon, I'm pumping air into it, right? So the change in the amount of, let's say, air molecules in it over the entire volume is given by how much is flowing into the balloon, right? So volume change in a quantity is given by the net flux of it across its boundary, basically. So the divergence theorem is just a conservation law. Okay. So please, if you're more interested in this, look it up in, let's say, in our given textbook, or even just in general in any vector calculus book. Okay. Now noting that because this domain is actually the volume, this is also often represented by a triple integral right here, like so, volume ke upar. And the boundary wala jo hai is a surface for 3D. So as an integral, double integral over the surface of a given body. So it can be represented either in terms of omega or gamma, or in terms of the volume and the surface, basically. Okay, so with this we've got our little background that we needed for this part of the course. So let's move on quickly to start considering our actual scalar field problem, which is of course the heat transfer or heat conductivity ka. जिसके अंदर our scalar field problem of interest is the temperature, or we'll come to that in a second. So we're looking at a two-dimensional body like so, and it's in steady state. So it's not, we're looking at a problem जिसमें कोई time dependence नहीं है. ठीक है जी. Now consider that this body has some heat source S. That is producing or providing some sort of heat to the body at a given rate. Let's see. So if we want to first derive the strong form of this problem, then we need to go back and consider our infinitesimal element like so at any point in the domain, and look at the heat flowing into it and out of it, ताकि हमें पता चल जाए of course कि जितनी उसके अंदर जा रही है, और the difference between how much is leaving it and how much is coming into it must be equal to the heat that's being produced within it, right? Conservation law से. So then let's consider, so heat flux agar hum, of course it's a vector as I said, so that's why it depends on the direction in which we're looking at. So there will be a heat flux in the x direction qx, and there will be a heat flux in the y direction qy. अब qx जो है अगर हम एक infinitesimal element को देखें, that is flowing through a length of dy. ठीक है जी, whereas जो qy है that is flowing through dx. So if I see the heat flow coming in from the right hand side, then that is given by the product of qx multiplied by dy, because the heat flux is per unit area, okay, or per unit length for a 2D problem. So right hand side से total heat जो अंदर आ रही है वो है qx times dy, or from the bottom surface the heat that's coming in is equals to qy times dx. Okay. Similarly, the heat leaving from this right hand side boundary right here now, sorry, पहले I should have been saying from the left hand side जो आ रही है, right hand side से जो leave कर रही है, that is actually qx, but added on top of it the small change in qx जो हो रहा है. So over this infinitesimal element there can be a change in the heat flux. So outside जो जा रही है, that's now जो original आ रही थी plus the change in qx over this infinitesimal element. Again, acting over an area of dy, so multiplied by dy will give us the total heat that's leaving. Similarly, top surface को भी इसी तरह हम consider करेंगे कि there is now a small change in qy. ठीक है, so I can write out this entire expression and notice that there will be some heat production also happening. So लेकिन overall there can be no change in the overall heat must be conserved or energy must be conserved, which is why however much is flowing out must be equal to the heat being produced. Okay, so this can be written in this way where ये individual terms है. This is the heat flux because of heat flowing in because of qx, heat flowing out because of qx plus del x, heat flowing in because of qy, heat flowing out because of qy plus del qy, and then finally plus the heat being produced because of the source. Now this source is given as heat produced per unit area, which is why it has to also be multiplied by the area of the element over which it is acting. Now all of this must sum to 0, and if I simplify it I can see that ये qx's wale terms will cancel out and qy wali bhi, and all I end up with is the small changes in the heat flux must be equal to the source within the element. So this is what I end up getting essentially. Okay, now recall कि ये del qx by del x plus del qy by del y, this is something that we already know what it is. This is the divergence of q. So I can write this as del dot q. ठीक है, del dot q को जब expand करें तो I get this. It's the divergence of q. Okay, so I can write it in vector notation like so. So del dot q minus s is equals to 0. Noting of course कि ये जो s है, this is a scalar variable. Okay, heat source जो is just a scalar. Okay, so this basically gives me the conservation law, which is the physical law which must be fulfilled for this heat conductance problem. Great. Next, as you may recall from continuum mechanics principles, that this is the physical law, but then physical law के ऊपर कुछ मज़ीद constraints impose होते हैं by different particular materials. So we can also have a material law, constitutive material law, जो हमें बताता है कि let's say कि एक body के अंदर ये heat flux जो है ये किस तरह है, how is that represented for a given material. So in this case, this material law is given to us by Fourier's law, or Fourier's law जो है basically it tells us how the heat flux in a body Q is related to the temperature gradient within the body. Okay, how the heat flux Q is related to the temperature gradient of a body. That is what Fourier's law is, and आपस में they are related by the variable k, and k here, sorry, not the variable k which is a material constant referred to as the thermal conductivity constant, या फिर most often represented called the thermal conductivity constant, right? So this is the case for 1D कि अगर 1D में होता तो फिर से सिर्फ flux in the given 1D direction would have been equal to minus k times the gradient in that direction. लेकिन 2D के अंदर we then have a gradient in the x and the y direction such that the flux is actually represented by related to the temperature gradient by a 2 by 2 material property, 2 by 2 matrix जो material property contain करता है, and that relates basically has the thermal conductivities kxx, kxy, kyx and kyy respectively, essentially telling us how the temperature gradient in one direction affects the heat flux in a given direction. Okay. Now, agar anisotropic material hoga, then all of these will be different. But if it is an isotropic material, then things simplify a little bit. We will discuss this later when we look at a particular example. Okay, so we can substitute this Fourier's law into our conservation law right here, right? Q is equals to minus d del T. और इसको हम इसके अंदर जब substitute करें, then I just get this expression right here. ठीक है जी, I could take out the minus such that rearranging it and then also representing the dot product in terms of its transpose matrix notation so that I can write all of this in matrix notation like so. Now this equation right here is actually the strong form of the heat equation, that is the governing partial differential equation for the heat conductance problem. Of course अभी भी कुछ चीज़ें missing हैं इसमें which are primarily the boundary conditions. So remember कि strong form के अंदर it's the governing partial differential equation and the boundary conditions that we have for a given problem. Okay, so what are the boundary conditions here? Now for the boundary, ये हमारी अगर पूरी boundary है तो हमारे पास दो boundary conditions हो सकती हैं. Either we will know the temperature acting on some parts of the boundary, or we will know the heat flux on some parts of the boundary. Okay, so wherever we have the temperature, we refer to it as gamma T, that is वो part of the boundary जिस पे temperature known है, और जहाँ पे flux described है, that is gamma Q, that is the part of the boundary where the flux is prescribed. Now for this problem, our essential variable or our field variable is temperature. Okay, so our essential boundary conditions are on the temperature, whereas my natural boundary conditions are on the flux, which is why this Q flux variable की जो है, ये gamma Q जो है, this is my natural boundary basically. Okay. These can be written out exactly in this way कि T is known at gamma T and the जो boundary condition known है उसको bar से represent हो रहा है, and the flux is known at gamma Q such that flux by the way coming out refer किया जाता है, इसलिए Q dot N के तौर पर उसको हम prescribe कर रहे हैं basically. So that is known to us and is given as Q bar. ठीक है जी. प्लीज़ नोट कि एज ऑलवेज हमारी पूरी बाउंड्री के ऊपर या तो एसेंशियल बाउंड्री कंडीशन गिवन होगी या फिर नेचुरल बाउंड्री कंडीशन. ठीक है, सच दैट any one part of the boundary will only be part of either the essential or the natural boundary. Okay, so that if I find जो मेरी पूरी की पूरी boundary है वो या तो gamma t पे होनी ज़रूरी है या gamma q पे. ठीक है, सो आई कैन बेसिकली ये कंडीशन को हम ये यूनियन की रिप्रेजेंटेशन में लिख सकते हैं. ठीक है, टोटल बाउंड्री consists of the boundary on which the temperature is acting and the boundary over which the flux is acting. Okay. Yes, Fourier's law को यूज़ करके हम essential boundary condition को उसी के अंदर substitute करके एक और तरीके से भी represent करते हैं. Not very important. Okay, so as I said, temperature is the essential boundary condition and flux is the natural boundary condition for this problem right here. So overall, my entire strong form essentially consists of a physical law, which is then manipulated by the particular constitutive material law to give the actual governing equation फॉर दिस प्रॉब्लम. और उस गवर्निंग इक्वेशन की ये दो हमारे पास एसेंशियल और नेचुरल बाउंड्री कंडीशंस हैं, एंड दीज थ्री टुगेदर मेक अप द स्ट्रॉन्ग फॉर्म फॉर दिस प्रॉब्लम. ओके, सो इस स्ट्रॉन्ग फॉर्म से हमें हमारी एज बिफोर फाइनाइट एलिमेंट मेथड को सेटअप करने के लिए वी नीड टू फाइंड द वीक फॉर्म फर्स्ट. सो वीक फॉर्म के लिए हम वही पुराना प्रोसीजर फॉलो करेंगे, दैट इज़ वी मल्टीप्लाई द एंटायर स्ट्रॉन्ग फॉर्म बाय एन आर्बिट्ररी वेट फंक्शन W. Okay, just that the thing that I want to focus of importance is that as before, this arbitrary trial function is a scalar for this problem. Why? Because remember that the trial function is some sort of, it corresponds a little to the field function, right? इस case में हमारा field variable is temperature. So temperature is scalar, which is why इस case में हमारी trial function भी scalar ही है. तो हमने उससे मल्टीप्लाई किया एंड देन वी इंटीग्रेट द एंटायर इक्वेशन ओवर द डोमेन. ठीक है, सो W मल्टीप्लाइड बाय द स्ट्रॉन्ग फॉर्म इंटीग्रेटेड ओवर द एंटायर डोमेन. ओके, ग्रेट. देन हमारे नेक्स्ट स्टेप्स क्या होते थे आफ्टर दिस? ऑफ कोर्स वी यूज्ड टू यूज इंटीग्रेशन बाय पार्ट्स to shift the derivative from one to the other, right? Abhi basically what the small difference right now is कि मैंने Fourier laws से Q को manipulate नहीं किया हुआ. Also just remember that I'll just write it down कि असल में this strong form right now is second right. Fourier law भी है, तो temperature के terms में this is actually a second order differential equation. Okay, so then we used to use our integration by parts to shift one order of differentiation from from our essential field, from our field variable temperature onto the arbitrary trial variable W. तो इसलिए हम इंटीग्रेशन बाय पार्ट्स करेंगे. अब इंटीग्रेशन बाय पार्ट्स जो है ना इधर थोड़ी सी कॉम्प्लिकेट हो गई है. उसके लिए लेट्स एक्चुअली एक्सपैंड दिस आउट टू कंसिडर कि ये जो मेरी पहली टर्म है इसको अगर मैं इंडेक्स नोटेशन में लिखूं, दैट इज़ इन टर्म्स ऑफ द रिस्पेक्टिव कंपोनेंट्स, फिर वो क्या, व्हाट डज इट लुक लाइक? सो इफ़ आई डू दैट, प्लीज़ नोट कि ये del डॉट q जो है, the dot product of del and q, the divergence of q is actually del qx by del x plus del qy by del y. ठीक, so there's a summation right here, so it's as if I can consider this integration separately and this integration separately. ठीक, और इसके ऊपर हम अलग अलग के ऊपर ज़रा इंटीग्रेशन बाय पार्ट्स अप्लाई करते हैं. तो that basically looks like this expression right here, जिसके अंदर आपको याद होगा इंटीग्रेशन बाय पार्ट्स में क्या होता था, dB by dx multiplied by a. So if I was integrating this, then I would get AB, right, minus what? dA by dx times b. I hope this is correct. Okay, yes. So ये जो a b है ना, इसके ऊपर मुझे फोकस करना है एक्चुअली, कि इसको I can also write it down as this d of a b with respect to dx. Right, so differential of AB with respect to dx को अगर मैं इंटीग्रेट करूं तो फिर मुझे AB मिल जाता है. ठीक है ना? So dAB by dx की इंटेग्रल over dx gives me AB. सो बेसिकली व्हाट आई हैव डन हियर इसके ये पहला वाला टर्म था ना, ये ए बी वाला टर्म, उसको मैंने इस फॉर्म में लिख लिया है इन दिस इक्वेशन. दैट्स व्हाई आई हैव गॉट del of wqx with respect to del x integrated over the domain. Okay, so please consider this expression right here and compare it to the one right here on the top right of the screen. If it's unclear, I'll deal with this in the Q&A later. लेकिन again ये दो अलग अलग integrals हैं, hence why I have it for wqx but also for wqy. Okay, and then minus जो right hand side वाली term होती थी which was just dA by dx, मतलब कि पहली term का a का जो मेरा w है इधर उसका differential multiplied by जो b था, so which is qx और y वाली direction में qy. Okay, so this entire expression is what we have in the for integration by parts in 2D. I can rewrite this in vector notation so that I have के जो ये मेरी left hand side थी w del dot q, that is w divergence of q, this is actually equals to del of wq. Again अब इस चीज़ को मैंने vector form में लिख दिया है, del dot wq minus what is this now, del w dot q. Okay, unnecessarily complicated, but yeah, again for more details for integration by parts in higher dimensions please do refer to the textbook. मैं इसके ऊपर बहुत ज़्यादा इसलिए नहीं फोकस कर रही, इसलिए क्योंकि अगेन दिस इज़ अ फाइनाइट एलिमेंट मेथड कोर्स, not an advanced mathematics course or vector calculus course. So if ever we do need to use integration by parts in higher dimensions, I will always provide you with this expression right here. Okay, this will be provided to you. So integration by parts in higher dimensions will be provided. ठीक है, जिस तरह आप लोगों को 1D वाली this was also provided to you as before. ठीक है, तो जिस तरह ये provided थी उससे ही तरह आपको ये वाली provide होगी. Please note कि वो in terms of flux exactly नहीं मैं आपको दे दूँगी ताकि आपके सारा कुछ ही काम आसान हो जाए. It will be just in terms of a vector variable. Okay. So once we've got integration by parts, फिर हमने क्या किया है, हमने we've shifted essentially one of our derivatives onto our trial function w right here. अच्छा, next what we can do is कि हमें याद है कि मैंने आपको divergence theorem ऐसे ही तो नहीं मेंशन किया था इस लेक्चर के शुरू में, so there is a purpose to that, which is basically कि the divergence theorem essentially consisted of कि the volume integral of the divergence could be written in terms of the surface integral. So essentially in this equation right here we have a divergence का volume integral. Look at this one carefully. इधर क्या हो रहा है, del dot this term, so del dot तो divergence होती है, तो ये divergence का volume integral निकल रहा है. That means that I can use my divergence theorem on this to manipulate this and convert it from a domain integral onto a surface integral, ठीक है, या फिर boundary integral. So if I use my divergence theorem, I basically get this volume integral or domain integral can be written in terms of a surface integral like so. Okay, अब इस expression को मैं already basically इधर से मैं शुरू हुई थी and I've started to manipulate it. I performed integration by parts and then I've used my divergence theorem on it. ठीक है, अब इस एक्सप्रेशन को, ये जो सरफेस इंटीग्रल है गामा, इसको भी हम मज़ीद मैनिपुलेट कर सकते हैं बिकॉज आई नो कि मेरी जो टोटल गामा है, टोटल गामा दैट एक्चुअली कंसिस्ट ऑफ द फ्लक्स बाउंड्री एंड द टेम्परेचर बाउंड्री. तो मैं इसी को ब्रेक डाउन कर दूंगी इनटू एन इंटीग्रेशन ओवर द फ्लक्स बाउंड्री प्लस एन इंटीग्रेशन ओवर द टेम्परेचर बाउंड्री, नथिंग एल्स फॉर नाउ. ठीक, नेक्स्ट नोट कि जो फ्लक्स बाउंड्री है ये तो हमारी नेचुरल बाउंड्री कंडीशन थी ना, इधर तो हमें हमारा क्यू पता है, दैट इज़ It's where our known flux is acting. So I can write this integral down in terms of the known boundary condition. ठीक है जी, ये known boundary condition जो gamma q पे act कर रही थी. So that this expression becomes this one right here turns into this one in terms of the known flux, known boundary condition. ठीक है, leaving the temperature boundary as it is. Okay. अब जब हमारे पास ये सब कुछ आ गया है तो फिर मुझे यही सारी एक्सप्रेशंस को सब्सटीट्यूट करने दें वापस मेरी स्ट्रॉन्ग फॉर्म के अंदर. बेसिकली मेरे पास एक ये इक्वेशन आ गई है नंबर 3 जो कि इस सरफेस इंटीग्रल को एक्सपैंड कर रही है. मतलब ये कि मैं उस सरफेस इंटीग्रल को इसके अंदर सब्सटीट्यूट कर सकती हूँ. ये जो था वाज इक्वल टू दिस, तो इधर इधर वो चला जाएगा नंबर 2 के अंदर, right? Or finally this was the left term on my total strong form. So after all of this manipulation I can substitute these equations 3 and 2 into my equation 1, that is my entire strong form, so that I get this expression right here. प्लीज़ इसको अपने आपको कंफर्टेबल बनाएं. प्लीज़ गो बैक एंड लुक एट इट. बेसिकली वो जो लेफ्ट हैंड साइड टर्म थी, पहली टर्म जो थी स्ट्रॉन्ग फॉर्म में, दैट बिकम्स दिस वन after integration by parts and substitution of the natural boundary condition. That turns into this. Sorry, integration by parts, divergence theorem, and then substitution of the boundary conditions. It becomes this. और right hand side एक source term वैसे का वैसा ही feature कर रहा है. Okay. Now note कि हमारा W, the trial function, was arbitrary except for one little caveat that we always have, which is कि जो weight function है W, that has to be 0 wherever we have the essential boundary condition applied. ठीक है जी. तो essential boundary condition तो हमारी इस प्रॉब्लम के लिए टेम्परेचर है. दैट मीन्स दैट वी आर सेइंग कि जहाँ पे भी हमारे पास गामा टी है, दैट इज़ जहाँ पे भी हमारे पास टेम्परेचर बाउंड्री कंडीशन है, वहाँ पे W मस्ट बी ज़ीरो. सो गामा टी के ऊपर हमारा W इज़ ज़ीरो, which means कि ये वाली पूरी term disappears and I only end up getting my 1, 2, 3 terms which I can rearrange so that as before मेरी temperature essential variable वाली सिर्फ और सिर्फ term जो है वो left hand side पे रह जाए, बाकी सब कुछ right hand side पे चला जाए. और please note, मैंने पहले भी आपको कहा था कि ये Q के अंदर मेरा डेल टी फिर रहा है जो मैंने अभी तक लिखा नहीं है क्योंकि unnecessarily populate हो जाएगी ये मेरी equation. So I've just kept my temperature जो essential variable वाली field है on my left hand side, बाकी सब कुछ मैं right hand side पे ले गई हूँ. उनके अंदर कोई temperature नहीं है, इसकी वजह से I can write down my manipulated expression like so. Now finally I'm going to substitute in my Fourier's law. ठीक है, so that my entire equation becomes this one right here. ये डॉट प्रोडक्ट को ट्रांसपोज वाली नोटेशन से लिख लिया. सो डेल W ट्रांसपोज Q was minus D del T, so minus से minus cancel, so just D del T. And this equation right here is my weak form for the heat conduction problem. Okay. And our aim basically is to find a solution for an approximate T, that is for TH, such that it satisfies this above equation for any arbitrary W with only one condition, that W has to be 0 at the essential boundary. ठीक है जी. सो हमारा एम ये है कि हमने इस वीक फॉर्म को सॉल्व करना है. एंड एज बिफोर वी विल, आफ्टर वी गॉट अवर वीक फॉर्म, देन वी विल यूज अवर Galerkin approximation and discretize the domain and so on and so forth to basically get to where we want. Okay. So just a few side notes for this weak form कि ये जो हमने strong form of heat equation थी, this is the strong form. This actually takes a well known form essentially कि ये जो strong form के अगर ये source term 0 हो, then this expression is known as the Laplace equation. लेकिन अगर S non-zero हो, then it's known as the Poisson's equation. और the reason why this Laplace and Poisson equation का नाम दिया हुआ है इसलिए because there are a number of problems in the physical world which have a governing equation which looks like this. ठीक है, सो द पॉइंट बीइंग कि हमने जो भी ये हीट वाली प्रॉब्लम के ऊपर सारा का सारा एनालिसिस किया है, अगर कोई और फिजिकल प्रॉब्लम होती विच इज़ आइदर हैज़ लैप्लास और पॉइसन इक्वेशन एज इट्स गवर्निंग इक्वेशन, देन उनके लिए भी यही स्ट्रॉन्ग टू वीक कन्वर्जन काम करती, और फिर आगे भी जो कुछ हम उस वीक फॉर्म के साथ करेंगे इट वुड ऑल्सो बी एप्लीकेबल फॉर एनी ऑफ दोज. So a number of examples for other physical problems which take the Laplace or the Poisson's equation इसके हीट कंडक्शन को हमने ऑलरेडी देख लिया, जिसमें फील्ड वेरिएबल टेम्परेचर है, मटेरियल कांस्टेंट जो है हीट कंडक्टिविटी है, और फ्लक्स वेरिएबल जो है हीट फ्लक्स होता है. कोई और प्रॉब्लम अगर हम दें मिसाल के तौर पे इलेक्ट्रोस्टैटिक्स वाला, उसमें फील्ड वेरिएबल वोल्टेज है, मटेरियल कांस्टेंट इज़ आर डाइलेक्ट्रिक कांस्टेंट, एंड देन फ्लक्स वेरिएबल जो है वो हमारी इलेक्ट्रिक फील्ड होती है. तो इस तरह की और भी बहुत सारी प्रॉब्लम्स हैं. सीपेज के लिए ये पोटेंशियल फ्लो, again these are not quite from my field, so I am not completely certain what the stream function exactly is basically, but they are applicable to other physical problems. So as I said, any method that we apply to solve this heat problem then can also be used for any of these other problems listed above. Okay, so after this we will move on to actually the first step of our setting up our FEM equation, which is that we need to discretize our domain. So I'll deal with that in part 2 of this lecture.